这个我看看啊，你们 linear algebra 有上 ODE？
是 combine 学，你要去把这个 complex
你们数学是哦，OK，你们 first year 没有学 linear algebra？first
combine 成你要去把跟 complex 呢？
year 啦，first year 就上这个了
可
，OK，就是
可能要是
这个应该我 try 看，这一是第哦，这个不是那个 PDF 是吧？
有
就是这样，但是早上99，这399，299，309，对啊，你看这个，你看，嗯。first of all，你第一个要懂的是 matrix 和 vector 会给你一个 vector 嘛，对不对？现在我们的工作是说要把所有这种 function 都可以写成这种 A 的 form。哎，we say A represent F，这就是那个 matrix representation 嘛就是这个东西啊。所以你的那个 bra 是一个 linear map，所以如果是 map between 个 finite dimensional vector space 的话，then 你就会有一个 matrix representation，这个就是那个 representation。对，当然没有例子。对啊，这边的例子比较，
这个问
bra 是也是个 vector，它是那个 function space 里面的一个 vector，所以你要问你自己 vector 是什么，所以我有 define vector 是什么，有吗？vector space，所以你的 function 也会符合那个 vector 的所有特性，你也可以加，也可以乘，什么都可以。它自己也是个 vector，但是它不是原本那个 vector。我们是把一堆符合那个10个条件的东西叫成 vector，它是一个 vector space。你的 vector 不是那个 Rn 的 vector，你知道吗？那 vector 是一个 abstract 的 vector space 来的这里，那这个 vector space，Rn 是其中一个 vector space，所以 Rn 里面的东西也叫 vector，只要符合这个条件的东西都叫 vector。linear map 可以是个 vector，但是那个 vector 不是 Rn 的，它是活在另外一个世界的。
因为它符合那个地，
对，要符合这10个 property。
我们就可以 individual 写成一个 bra，因为它符合那个 properties。
没事
好像在 physics 我们也写成一个 bra individual 的 bra，
啊。
那个 bra 可以 represented by matrix，
然后
so 那个 bra 是 vector。
下去，但是它跟那个原本的那个 cat 的 vector 不一样，活在不一样的世界里面。他们两个都是从 vector space 来，但是不同的 vector space。你看这里就给你2个 example of vector space，不一样的 vector space，一个是 polynomial form 的 vector space，一个是 matrices。所以你的 bra 其实是一个 vector space of matrices，因为它有 matrix representation。 Okay, we will continue. I think we're gonna speed up a bit, so that we can catch up the syllabus. So if you think that's too fast, you don't understand, just feel free to stop me. Okay, yeah. Okay, so what we're gonna do first is we're gonna prove these Hubert noun statement that we left from last week. Okay, so we're gonna prove Hubert noun statement. Okay, wait, let's prove the statement from Hubert noun statement. Okay, which is the Hubert zero theorem or zero set theorem, zero set theorem. So inside this statement, right, very important assumption is our field is always assumed to be algebraically closed. And last time I proved that if it is algebraically closed, actually this field is infinite. It's infinite. Okay, so first statement we're gonna introduce is the correspondence between points and maxima ideal. So there's a bijection between points and maxima ideal. Points and maxima ideal. Okay, so what we're gonna do first? First, we're gonna just pick some subset of polynomials from polynomial ring of n variables. Okay, and set of maxima ideal. So this set of maxima ideals are not chosen randomly. So these maxima ideals should contain S. Okay, obviously it's a subset of the polynomial ring of n variables. Okay, so we claim that if you consider the zero set of S, right? So remember that this zero set of this S is also equals to the zero set of the ideal generated by this S here. Okay, we have proven that. So there's a bijection between set of maxima ideal. Okay, so what's this bijection here doing here? So we're gonna send all the zero here, okay, A1 up to AN, to the ideal generated by x minus A1, x minus A2, S1 minus A1, S2 minus S2 until xn minus AN. So basically you take all the factor xi minus AI. Oh, wait, this is not maxima yet. Okay, so last time we said that ideal generated by these x factors of xi minus ai is maximum. Okay, because it's the kernel of a evaluating homomorphism. Okay, where you evaluate to the scalar field. So if you are kernel of this such map, it must be maximum. Okay. A ring quotient by a maxima ideal is a field. Okay, so the claim is this map is bijection. It's bijective. So bijective, you need to show two things, right? Okay, you need to show that it's injective, surjective. Okay, this map. Injective, surjective. Maybe you want to check. Okay, we already checked that this map is this map mapping into the right space, right? Is maximal. And what else we need to check? Oh, okay. So you see, you don't just map into maximal ideal, right? This maximal ideal have to contain the original S. Okay, so uh, you reckon that why this ideal here will contain all the S's here? Where you get these points from? This point have to vanish on all the function in S. In particular, what? This point is a root for all the function in F. Okay, does that make sense? Okay, so let's call our point P. Yeah, let's call our point P. And then we just now verify that phi P is already maximal. Okay, kept using the evaluation homomorphism. And then, not that, this phi P should contain your S. How to show this? Since for every function in S, Fp have to be 0. And also, more importantly, our field is algebraically closed. Okay. So you can pull up the root. So you can use a statement like fundamental theorem of algebra. Okay. So did we give a name to this set? Yeah, Ux here. So it follows that we send it to the right maximal ideal that contain X. Okay, so it land in the right codomain here. The other thing we need to show surjectivity and injectivity. Okay, so let's do surjectivity first. So if we do surjectivity, then we will take any such maximal ideal, mu x. Okay. Uh, then we want to show that what? There's a point, okay, that map to this mu here, this m here. Which point you need to pick here? Actually, quite obvious, right? Because every maximal ideal inside here, okay, how does it look like? It is actually generated by a bunch of factor xi minus ai here. Okay, xi minus ai here. For these ai live in a and n affine space here. So there are two an you need to bear in mind whether I'm talking about the polynomial ring or I'm talking about the affine space. Okay, so you need to be careful. Let's talk about an here. And similarly, we know more things, right? We know that there's a S contained in this maximum ideal here. Okay. But what does this imply? This actually implies that the point A1, A2 up to AN actually live in the zero set of X. Okay. Then this is the point you're gonna send to. Okay, given a maximum ideal. Maybe you will ask me, why all the maximum ideal look like this? Actually, this is what something we proven last time. Okay, all the maximal ideal should look something like this, x minus a. When we finish up the commutative algebra part, you should look it back. Okay, so this then here is not trivial. Maybe I make it. This one not trivial. Where we did in the commutative algebra part. Okay. Okay, no. So you need to settle why your maximum ideal looks like this. If it look like this, then good. You just take the AI to be your preimage. And the point AI to be your preimage. Okay. Next, we're gonna show injectivity. So what do you do with your injectivity here? So suppose you have 2 points, AI, and another point, BI. So these are the points in ZX. Okay, then you suppose that phi of P and Q is the same, okay, for some maximum ideal. Okay, but the image of these two is different, right? Okay, one of them contain xi minus AI, the other one contain xi minus bi, but they live in the same ideal. It's closed under addition, closed under scalar multiplication. So, well, for each I, we should have xi minus ai and xi minus bi living in B together, right? In particular, ai minus bi is inside your ideal, right? Your ideal closed under addition. But could this ai minus bi be something else? If this difference is a unit, what happened? Your maximum ideal is actually the whole ring. Okay, so in particular, this should imply that AI equals to BI must be 0. Okay, otherwise you will always get the whole ring. Okay? Otherwise, this maximum ideal is the whole ring, which we don't want. Okay, no? Yeah, whenever you got a unit, because these AI BI are coming from where? A, right? K is a field. Okay, every non-zero element in a field is a thing. Okay, if you have unit inside your ID, what happened? You will create 1, because you can take the inverse, multiply to the unit. Then your 1 appear in your ring, then you get the whole ring. Okay. Okay. So this is the first part. So there's a 1-to-1 bijections correspondent between points and a maximum ideal of that point. Okay. So what do you imagine here? So let's say you have let's say z of y minus x squared here. Okay, z minus x squared here. So these are all the well, I mean this I mean, so this is a real picture, right? This is not algebraically close. Maybe you should imagine it as a complex picture again. Okay, if you imagine it as a complex picture, okay, you get some quadratic surface, right? Then every point should have a projection to maximum ideal of that point. That's all. That's what this theorem trying to say. It's a 1-to-1 projection. Okay. Maybe now you might see it is quite trivial, but later, when we have more property that we can discover from the ideal side, actually you will recover some property on the geometry side. Okay. For now, we just know that there's a 1-to-1 bijection. This 1-to-1 correspondent is very special because 1-to-1 correspondent means what? One point only get attached to one maximum. Okay, so everything that you can say about this maximum ideal potentially will give you some geometrical meaning on the point on geometry. Yeah, no. For now, you haven't seen it. Just we create a bridge between these things. Okay. All right. The second statement is what we call the weak. Now, Stellen's up. So basically, what does weak null Salazar do? It tells you that if you have an zero set of an ideal which is empty, actually your ideal must be the whole ring. That must be the whole polynomial ring. Okay, so how do we write this down? So if Zi equal empty, then I must be the whole ring. If you look at the, this is the polynomial ring. If you look at other reference, I mean different references, they will provide you the contrapositive of the statement. It's the same, right? Contrapositive. So you say that if your ideal is proper, then your zero set must be non-empty. Right? This is the contrapositive of this thing. Make sense or not? Yeah. If you are proper ideal, your zero set must be something, must contain something, some non-trivial. Okay, so how are we going to prove this? Well, actually, we're going to prove this using contrapositive. So we'll prove it using the usual, the other statement, equivalent statement of it. So we suppose that is not the whole polynomial ring. So what do we do here? Well, we consider a set of all proper ideals, okay, in the polynomial ring. Let's say the AN that contain I. Okay. Well, what can you do here? We know that our ring is actually Noetherian. Yeah, our ring is actually Noetherian. So this means what? This J set here, this set of J here, will have actually a maximal element. Okay, we'll have a maximal element. In fact, this maximal element in this chain of ideal here is actually a maximal ideal. Okay, that contain I here. Then by A, you will find something inside your zero set. Okay, in particular, the special point of that defines this maximum ideal. And the special point that defines this maximum ideal should be this. Okay. Okay. Any question? Okay. Let's continue to the last most important one. Why radical ideal makes sense here. So the third part is called the strong noun stanzat. Okay. So what does the noun strong noun stanzat says? So if you start with any ideal, let's start with any ideal, and then you look at the zero set of this ideal, and then look at the ideal of this zero set again. What you return is not J, but instead you get radical of J. Okay. Last time I provide you an examples, right? So if you have a function that can split into power of function, you want to make that function zero. So every factor should be zero also first. So you must have the basic factor to vanish on your zero set. Okay. All right. So how are you gonna prove this? So I mean, one direction is obvious, right? Which direction? Which direction is obvious? There's one direction is obvious. Think about it. Try. Okay, fail, never mind. Don't fail in exam. Fail here. Okay, so what's the which direction is easier? Think about it. Left to right or right to left? I'm gonna try. Anyone got idea? I'll try Faiz. From right to left, yes. Okay, so first, let's try. How do we show that? We have root j is always a subset of I z. J, why? Since if uh, there's some n such that f n p equals 0, this is the example, like the example I told you, right? This implies what? Fp have to be 0. Okay, why? Actually, there's some very important idea here. What's this idea here? You have a product of thing equals 0, then one of the factor to be 0. Integral domain. Okay, so because what we consider is a field which is an integral domain. No, FP is already a point, right? Yeah. FP is already evaluated. Okay. Right. So for the other direction is a bit trickier. Okay. Actually, there are few proof, and I post some version of the proof on the Moodles if you're interested. For now, we will use a trick which is quite useful for various places actually. What's called the we will use a Rabinowitz trick. Okay. So well, what we're gonna do? Suppose f is a function that we take or polynomial we take from a. Should we take from square root j? Well, let me check. I'm doing something stupid here. Let's simply just take from j first. Wait, why do I start with square root j? I think something wrong here. So we just take any function from the where from the izj first. Okay, we want to show that f is in the radical of j, which means that there exists some n such that fn is in j. Okay? So we're going to show that to some power actually live in j. F itself doesn't have to live in j, but f to some power live in j. Okay, so this is the point of square root j. Okay, no? Okay. Does it make sense? Everyone okay with this goal here? Okay. Forget whatever before, but can you understand this goal first? Okay. Okay, so we're gonna do this. So what's the trick here? So the trick here is we don't consider the polynomial ring of n variable, but instead we enlarge it. We enlarge it using a extra variable here called it t. Okay, enlarge it. Okay. So what we're gonna do here is we'll define a new ideal here. So what's this new ideal here? This new ideal here generated by Jn 1 minus Tf. Okay, so what does this mean? Actually, we are kind of like putting in the inverse of this f here. What's this f here? Yeah, inverse of this special f here. Okay, but I'm kind of putting in an extra inverse here of this f. Are you guys okay or not if I talking about inverse of f? 1 minus Tf. Why is it the inverse? If you quotient by this idea, right, you are adjoining T as the inverse of f. Okay. Yeah. Okay, so we consider this a larger idea here. Okay, inside this larger ring here. Sorry, this. Okay. So what's this zero set of this new ideal here? What's this zero set here? How do you choose the point that make this function? I mean the polynomial inside this new ideal here zero. Where are these points from? So well, first it should come from uh, an, right? So an. Okay. The other part obviously come from the t part. So okay, so just a1 here. So it's all the p and t such that you need to kill the every function in the ideal j and also kill the 1 minus tf here. So you need to measure that 1 is equals to, okay, maybe just write it, 1 minus t of fp is 0. Okay. So what you can see here, this t are actually quite dependent of your on your e, quite dependent. Okay, is it okay or not? Zero set of an ideal. You know what it means? Just all the point that makes all the function here zero. That's all. Nothing special 啊。Although you see very weird generator here，没有什么特别的，就是我要让这里的 function 变成零了。Is this what I'm writing here? The p make all the function j to be zero, and then the p and t that makes the other function to be zero. That's all. 就这样。Okay, make sense? Okay. So I haven't tell you what we're gonna do with this yet. So let's continue. This construction a little bit longer, but compared to the other proof, I think this is the shortest already. Okay, so I'll be patient a bit. Okay, so next, but we know that f is in I z of j. This implies that what? Fp should be 0 for all the p in zj. Okay. This is the definition of this I here. Okay, I of some point. How do you construct I of some point? You consider all the function that vanishes of this set of things, right? Okay. The set of z. So therefore, we argue that actually z of j prime is empty. Why is it empty? Why is it empty here? Why is it empty? Go back and look at your how you define your zj prime. Okay, you cannot think of no way. You need to go back to your definition. Okay, so you see here, this special condition here. If fp is 0, what happened? Why is 0? Contradiction. Okay or not? Okay. So there's nothing there. Okay, but by the weak Naus-Stellensatz, what does the Naus-Stellensatz tells you? The weak one. If you have a zero set of an ideal which is empty, means what? Your ideal is the whole ring. Where is the whole ring here? So meaning what? This new ideal generator is actually the big ring. Okay, it's the big ring. Here adjoint x1 up to xn and then plus n. It's actually the big ring. Okay, the ideal generator. So in particular, there's a very special thing, right? Whenever we see the whole ring, we are quite excited for one element. The element we are quite excited is the unit element here. the multiplicative unit. 1 is inside this ideal. Okay, 1 is inside this ideal means what? You can generate 1, okay, using the element inside J prime. Okay, how to generate here? How to generate? So I could write it in some multiple of 1 minus t times f. Okay, this f is the one I pick. So some multiple, what multiple is it? So this multiple, I should pick it from the polynomial ring. Okay, plus some other generator. Okay, where this generator came from? Let's call this generator Fi. This generator Fi. Okay, with some multiple also coming from the ring. So maybe there are finitely many of them. Well, I mean, you can only generate it using finitely many of them. And last time we talked about this finite sum inside the ideal. So this G, Hi is some scalar. Is it okay I call them a scalar actually? I'm sure whether it's okay. Usually scalar means a scalar field here, but now I just want it as a sum coefficient. And Fi coming from your J. Okay, generator of J. Generator of J. Well, so next, what we're gonna do is we're gonna do what I said just now. So consider 1 actually inside this large ring here, quotient by the ideal generated by 1 minus TF. So if you recall, what's this in algebra 1? What's this? This is just the polynomial ring adjoined with the inverse of F. Yeah, okay. Adjoined with the inverse of F here. So in this case, if I put this 1 here, this presentation of 1 here, into this ring, what happened? What do you think? What happened here? So there are 2 parts, right? So 1 part, 2 part. So I Q1 minus TF. Meaning what? 1 minus TF become 0. So the first part here contain 1 minus TF. So this part become 0. Okay. So I just left with the second part. Yeah, I just left with the second part. I mean, second part modulo something. Okay, if your turns out that the second part got something related to 1 minus TF, then you need to do modulo here. So after that, what do you get here actually? Then we will obtain that 1 is equals to the sum from 1 to m of Hi x1 to xn comma 1 over f times Fi times x1 to xn. So basically you replace your t by 1 over f, okay, inside this ring here. Okay, so well, what does this mean here? This means what? Your Hi contain these variables here, xi, sn, and 1 over f. Okay, and the fi just contain x1 over sn. Okay, so what we're gonna do here is something called the normalization. Okay, so you could imagine that this f, I mean this f, how to imagine? Let's say to make it a bit smaller, just look at this. Right. So well, okay, let's put s1, s2. Okay, so you can ask yourself, or let's say hi is x1, for example, x1 times x2. Okay, Then you can ask yourself, if this, then what is hi of x1 power f? What's this? Okay, so you just do substitution. Okay, but when you do substitution, what did you see? Actually, you see f in the denominator. Correct or not? Okay. But in this case, you have a multiple hi to consider. Okay, so it will appear in different powers, but these are just finite, right? Finitely many of them to consider. So, in fact, we can pick the largest one, call it Fn. Okay. So we can multiply this Fn across such that we replace these Hi, such that there's no more 1 over f variable. Maybe there's some multiple of f, it's okay. Okay, multiple of f. So this is in the ring of K joint Xn. Okay. So this means that we clear the denominator. Do I need to demonstrate you how to clear denominator or not? What I say is a very concrete thing. Take them to be the yes, power of f hearing in hi. Okay. Does everyone understand clearing denominator means? If you don't understand, I can write it to you. Clearing denominator. Where the I think it's the same thing, I guess. How many variables is it? And yeah, should be n. Yeah, sure. Yeah, sure. So this is same. Okay. Yeah, it's the same power. So clearing denominator, just let me quickly write down. Let's say h1 plus h2 is like x1 over f plus x2 over f squared, like this, right? Okay. Then if I want to clear this denominator here, what should I do? I can multiply both sides by, this is what I mean by clearing the denominator. But remember that, you see, on the first term here, I introduce an extra f factor on x1. Okay. Yeah, so yeah, we're just clearing the denominator. Okay, no? Okay. Okay. Cool down, cool down. Okay, next. Since okay, so up to here, what do we do? We write f to the power n as sum here. Sum of what? Sum of the multiple of generators in your J. Are we done yet? Are we almost done, or we almost done actually. Okay, we're almost done already. But now we just need to need to what? Need to put this element back to the right ring. Correct or not? Which is the right ring we need to put it back? We need to put it back to the smaller ring, right? We don't want this extra f equals there. So is this element here come from the smaller ring or not? This is what we want to argue now. We already clear all the denominator. Right? There's an example for you to imagine. So previously, okay. So okay, maybe we just use this example to think about it. It's easier. Okay, let's take this example to think about it. So previously, in this h1 plus hi here, this particular these two term here, These are living in K adjoint x1 up to xn and f inverse. Okay. But after we clear it, after we clear them, where does this function live in? So our claim here is we want it to live in the smaller ring that we started with. Hello. So the problem on doing this is like you need to make sure that there's one way to get to this element. If there are multiple ways, like the quotient, right? If you have some quotient, then maybe for example in the modular arithmetic, okay, let's say Z12, right? Okay, maybe the number 12 is coming from where? Coming from 0, then coming from 24. So we want to make sure that there's one way to get this 12. Okay, how to get this 12 in one? I mean, how to get it? There's one way to expressing this element in the smaller ring. So since we have a natural homomorphism from this K adjoint x1 up to xn, living in K adjoint x1 up to xn, adjoining the inverses, okay, is injective. What? Okay. And we know that this Fn here that we produce here is living inside this, we call it a J prime bar. So after we quotient by the ideal generated by 1 minus Tf here, so this is just the ideal under the projection map, or the canonical map. So under that map, what happens here? I minus Tf becomes what? 0. So this is just what? The ideal generated by J. Okay. This projection, yeah. So J prime live in where? J prime live in the large ring, right? So we have a projection map from this large ring here to this quotient ring. Yeah. Okay, this quotient ring. Yes. So we are looking at a J prime bar. Right? We're looking at a J prime bar inside this ring. So become a J prime bar. Yeah, correct. So we are looking J prime bar inside this quotient ring. Okay, we look at the larger ring and then we quotient out by some. I don't know. Okay. And then these two together will implies that actually this Fn is coming from the smaller ring. Okay. No other element will give this Fn other than itself. And this will imply that actually Fn is living inside J. Okay. Does it make sense? Okay, so this Rabinowitz trick is you introduce an extra variable, okay? Introduce an extra variable and then try and adjoin the inverse into your ideal. And then you just find that the 0 set is empty, and then if it's empty, then the new ideal generated is actually the whole ring. Yes. Say what? Oh, so this Rabinowitz trick, what does it do is you get your original ideal, okay, and then adjoin with the inverse of F. Okay, but when we say adjoin here, it doesn't mean the ring adjoining. You are adding a generator of 1 minus Tf. Okay. And then what do you do next? You look at the 0 set of this data here. Actually, this 0 set is empty. You cannot find the inverse actually. Correct, no? Because FP is always going to be 0. Okay. Now, so this means what? This means that your ideal that you generated by J and this new generator here is actually the whole larger ring when you adjoin with. And then next, you consider a quotient ring. Okay, quotient up by the ideal generated by 1 minus T. So meaning you generate the new ideal. Okay, cancel again, throw away the generator again. But the whole point of doing this is what's the whole point of doing this? The whole point of doing this is to find this presentation here of Fn. Why? Because if we have something related to 1 here, then it's nicer. Okay, we can express 1 as something else. Then you can use this 1 here to create Fn. Does it make sense? Does it make sense? Okay, once you get your 1 here, then you can create your Fn, because anything times 1 is the thing you want. Remember, it's a unique mark. Okay. Any question? Any other question? Yes. This part. Previous.
So can we just take P equals 0, just substitute it, and then
Yeah. I mean, well, you can do substitution, but the point here is what's the substitution means in mathematics? Why you just substitute and whatever you like? You understand? We're just trying to make it precise. Use the quotient way to make substitution precise. Yeah, I mean, this is the whole point of what A1 also, right? In the last part. Actually, when we do the isomorphism, checking ring isomorphism, those are just substitution, just the high school substitution you do. But the point here is why it makes sense to do substitution. You understand? It is actually a substitution. Morally, it's just substitution. You quotient by 1 minus T. Yeah, morally, it's just substitution. But the point is, why you substitute that one, don't substitute the other one. Right. And what substitution means? Why you can just change it. Okay. Yeah. So then isomorphism will make this precise. So what's the map you are using here? We can do different isomorphism using maybe same map. I mean, same substitution, I mean. Okay, now. Yeah. Cool. Before we finish, or before we finish, let me give some very crucial, important remark here. Okay, so first part here is notice that what's the zero set of x squared plus 1? What is this? In which ring? Very good. Tell me, what do you know about it? If inner is empty, right? Okay, but the ideal of but this ideal, well, I mean, but the ideal we consider here is a proper ideal of Rx. Okay. So just now says what? If you have an ideal that gives you empty set, it should be the whole ring. But here it's really proper. So here slash it. Okay. But if you consider in the algebraically closed set field, right, then this zero set here should have in minus I. Okay. Yeah, so it's a non-empty. The ideal is proper, and then the zero set is not empty. Okay, so the point here is upshot here is algebraically closed is really important for Hilbert Nelson Zatulov. force field. It's important. Okay. One last thing. Maybe two last thing. Okay, two last thing. Because the next part we want to jump to the other subject. Okay, two last thing. So second last is for this consequence of this Hilbert-Nernst-Stellensat. So Hilbert-Nernst-Stellensat is actually a form of a generalization of linear algebra. Okay, so what do I mean by that? So really, what this Hilbert-Nernst-Stellensat do is, it is a theorem about system of polynomial equation. In linear algebra, you just learn about linear equation, okay? But here you learn about polynomial equation. Okay, it's really something about solving a system of polynomial equation. It doesn't tell you how to solve, it just tell you whether to answer. Okay. Well, okay. So what do I mean by here? So let's take some finitely many polynomial inside a polynomial ring. So an here. Okay. So so let's say I give you a scenario here. If there exists some polynomial g1 gm, okay, in an as well, such that the gi fi, the product of gi fi, and then sum of them equals to 1. Okay. If you have this, what can you argue here? Then, is it obvious? It is obvious that the system of equation for all I equals to 1 m of fi or fi to be 0 actually has no solution. No solution. If you have solution, what do you get? Again, you get 1 equals to 0. Okay, so if you have this condition appearing, then you won't solve this fi actually. Okay, you won't be able to solve it. Okay. But at the same time, if this gi happens, what does it mean here? If such GIs appear, what does it mean? You create a 1, meaning what? 1 is inside your ring. I mean, your ideal. So meaning what? Implies that this fi actually generate the whole ring. Okay, so similar trick we used just now inside the proof of Hilbert-Nernst-Stellensat. Okay, so the 1, so the moral here, 1 is very important. Okay, inside your ideal, whether you have 1 or not. Okay, GIFI is a way to create element inside your ideal. If you happen to create 1 inside your ideal, then the ideal you generated is actually the whole ring. Okay, is the whole ring. So so what does Hilbert-Nernst-Stellensat says here? All together. So it will say that if such GI doesn't exist, okay, and if K is algebraically closed, then Fi is actually solvable when there's a solution for it. Okay, so another question you can ask here is, I given a bunch of Fi to you. You want to show that whether this kind of GI exists or not. Actually, there's an algorithmic way to do it. okay, which they use the Grosvenor basis. Okay, we won't do Grosvenor basis in this class. Okay, if we have chance to do commutative algebra, maybe we could do Grosvenor basis then. There's an algorithmic way to check whether this I exists or not. This GI. This GI exists is like something you finding the variable, right? Finding points that can solve this polynomial equation. Right? Like for example, if you want to solve a quadratic equation, right? You have formula, right? Quadratic formula. And then you can ask whether got a cubic formula or not. And then you could get not formula, but in this case, just algorithm way to solve it. There's no formula. Okay. So the extra here is Grosvenor basis. Grosvenor basis is an algorithmic way to determine the existence of GI. And actually, our Grosvenor basis is very related to other field already, like computer science, those stuff. It's very algorithm, and then very computational. Okay, so this is one way algebraic geometry can relate to different fields other than pure medicine through this Grosvenor basis here. Quite professional they do this Grosvenor basis thing. Human, it's hard for human to iterate these calculation, but it's really easy for machine to do it because the instruction is the same, but you need to iterate. Yeah, just iterate. And this is what machine good at. So the corollary is, so we have a bunch of bijection here, actually. So let K be algebraically closed. We have the following 3 inclusion reversing bijection. In a moment, I will tell you what is the including reversing bijection here. Okay, so bijection between what? So there are really 2 things we are looking at here. Okay, there are 2 things here. So one of them, both of them are AN, right? Okay, just depending is a subscript or superscript. Okay, so one is the subset of ANK, and the other one is ideal of ANK. How many kind of ideal I've shown you? How many kind of ideal? Can you give me the name? How many kind of ideal I've shown you already? Radical, prime, and maxima. You know what's the relation between them? Actually, in secret, I asked you to prove some proposition between them already. Okay, so maybe let's start with ideal. Okay, so what is inside ideal? I mean, 3 of them are kind of ideal. And I asked you to show that all of them are ideal. So first ideal we consider is actually radical ideal. I mean, not considered in this class, but first subset of ideal is radical ideal. And then we actually show that prime ideals are radical last time. Okay, and then well, in A1 we know that maxima ideal are prime. And by the way, this inclusion is not the inclusion reversing we're talking about. Later I will talk more about it. So we have a way to go from ideal to a subset of AN, right? Okay, so what do we do here? We can look at the 0 set, or if you give me a subset of AN, which I look for you some function that vanishes this point. Okay, not called F. This one is called I. Okay, and then Hilbert now tells you what this radical ideal, right, have a one-to-one correspondence with the algebraic set of AN. Primes, do you remember we proved a statement with primes? Ideal is prime if and only if the thing we introduced after topology. Irreducible. Okay, so there is a one-to-one correspondence with irreducible algebraic set, which we call the affine variety. Okay. And lastly, one is bijective with maximal ideal. Just now we proven already. Point. Yeah, just point. Okay, just point here. So where's the inclusion reversing talking about? So if you have a chain of ideal, right? Let's say I1 in I2 in I3 like that. Then remember that if we take Z, right, this is a inclusion reversing property. Okay. Similarly, if you start from 0 set and then you take the ideal, also inclusion reversing. Okay. Okay. Okay, so I will let you to finish the proof of this corollary. Most of them already we have gone through. Okay. Yeah, most of them we have gone through. There's a little part you need to finish on. Maybe I just write it down what you need to finish on. You need to finally check combining all the previous result and then check actually Z of I of Zx is equal to X for all X. Which n? Should be the bottom end. Okay. Yeah. Any questions so far? Any question? I don't expect you to like understand on the spot. It's not like that. You need to do your own reading. Okay. It's not like you understand now and you have to read it afterward. Meditate on it. And you need to meditate on it. Yeah. Okay. Any other question? Any other question? Quick question? Any quick question? No? Okay. Okay. Let's have a break until 1:14. 坐上去。喂，哪个？要去。
往下看。
哎，一层聊一层，你打到哪里啊
我上周还没怎么弄。
？OK，我觉得你重点看一些东西，你重点看这种 proof，看一下我有没有漏掉什么东西。
都要加上吗？
什么叫加？
就是这种 proof 你全部都要写。
看我有没有漏掉，减。如果我有漏掉，我补。但是这种东西我不会补。但是看这种东西我就有东西，就是我讲的，我的意思可以明白漏。只要确保我在 claim 没有漏东西，你慢一点打都不用紧，因为我要确保我的逻辑的是稳。
以前就可能6我看，他们各自各样去看，那天我看到不是好烦。就是我做那个 topology 的那个 assignment，这样的。对，个问题是我有没有办法从 Archimedes property 有一个 sequence，这就是有一个 condition，再讲讲，
你在什么 space 上面？在 R 上面？
在对，然后讲表示，
Dense 不是就会给你一个点了吗？当然 Dense 是从 Archimedes 来的
对，
，Dense 是从 Archimedes 来，然后 Dense 就会送你一个点了。
他会送我那个点嘛，对不对？那个点是被从那个点嘛，对不对？
只要有2个不同的点，前就会有一个点。
类似呀，是哦，
对，那个 Dense 确实是从 Archimedes 来。对啊，我们上次 proof Dense 就是从 Archimedes。
我没有办法，我可不可以用那个点来帮我做，就是把它变成一个 sequence？
当然可以啊。你要什么 sequence？
我要一个 composition。
你要先知道你那个点是 limit point 先哦，等你才可以。喂，你现在是什么情况？我整个 set 都不知道是什么来的，我就要做 point 了，我可以做
就是那个 distance 嘛，那个一个 distance function，一个 real number，要 work on 那个 real number 它应该这样。
OK，
然后我现在要找的是这个 distance，因为这个 distance 这个 matrix 它是被 determined by 那个 element of 这个 R 对吗？不是，等等，matrix 是一个 real number 那样的东西，然后它里面的 element 是 determined by 那个 x 那个 matrix space，yeah，那个 x。
然后
我现在要做的是，这个 matrix 它越 converge 之后，就代表这个 x，它越这个 x m 越 converge 去那个 x，就是在那个matrix 里，我不知道我可以不可以讲。
你是说 SN convert to S 的时候，它的距离是不是越来越小啊？
就是我要从 matrix 那边，它2个距离越来越近，推去这个 xn converge 去 x。
这是 definition 啊，这是 definition 的嘞，不是 definition，这是 definition。conversion definition。
conversion definition。
conversion definition 是说 that exists n such that 小 n 大于那个大 n 过后，e of 那个 SN s 小于 epsilon 嘛，for 每个 epsilon 这个就是说 converge 的意思就是说，给你每一个 epsilon，then 会有一个大 n，而且所有后面的 term 和这个 s 都保持在这个 epsilon 里就这样。然后，
但是我现在有的工具是，我现在好像只有我要 show 的就是这个 conversion，我要 show 的这个，
所以 converge 它都 converge 了，这么你要说它 converge？
因为我是讲它的 distance 是 conversion，不是它的 distance，就是有另外一个 set，
另外一个 distance 是吧？
另外一种
then 你要说那一个 distance conversion，你要用 based on 刚才的那个 distance conversion。
其实不是，就是你给我那个方向是
有看，
可能我讲不太清楚，不好意思，我要讲好，不要讲好了一点，可能要给你看一下，不好意思，要这个就是这个最后的
对啊，这个是吧？是吧？这个
我要show 它是零
对，没有错，
就是要找到一个
没有错，就是你这边的 convert 是那个 dxy 小于 epsilon 的东西嘛？但是现在我要你说的是 dx n 逗号e 减掉 dx。
这个我已经 show 了，我要 show 的是那个 b。
你要说 b
我要 show 的是因为我要从这个
左去右，右去左，
左去右 所需
，OK，
所以我要 show 这个 x 是一个 limit point。
哦，
所以但是我现在就是
因为你这个等于零的时候，就代表这个等于零啊。
这个等于0，
但是 increment of 这个东西等于零是什么意思？
等于0。
就是有东西无限靠近，就是 dxy 这个号码无限靠近零，
是
这样的意思是什么
我
？d 跟这样的 x 跟想想啊，then 什么意思？
嗯
有很多 y 的点无限靠近这个 s
嗯
啊，
很多个 y 的点，
无限靠近这个 x，但这个 y 是在一的点呢，
还是在1的点。
然后这个 s 跟 y 不是同一粒点呢，因为如果同一粒点，这个 dsy 是零嘛，
嗯，
这样你有一个这样你的 s 不是
我的 s 还是 x
x 没有 s 在里面
哦 x
啊，x。
在哪里？在 x 里大 x 就是这个 topology 这个
对对对
matrix
对对对对对，我是说这个 S 点。
x n yeah
OK，从这边开始讲，从这个等于零开始讲，
嗯
这个等于零，这个等于零等于这个 increment 等于零嘛？这个 increment 等于零的意思是什么？
意思是我每个点都会无限靠，因为 by increment 的那个
property 对
丢了嘛，那个就是有个
，yeah
x
definition
yeah
yeah，然后有不同的 y
对啊，不同的
让它无限接近零这个号码。
y 无限点呀是对
无限接近的意思是什么？你就可以调你的 epsilon 哦，
啊是
就那个 increment 的定义，
对是
越切一点就有一个东西在那边，切一点又在
啊，这样你就
，then 这些 y 全部都是一里面的点第一，
嗯
因为它是从一里面选的 y。第二，这个 y 又不是这个 s，因为如果 y 等于 s 的话，这个 dsy 就是零了。所以什么意思？每一个 epsilon 你都找到一个
点
y1、y2、y3、y4、y5，越靠近这个 x。
对
then
呀
什么？
我主要是因为这个 x 段它是我讲想啊，就是因为它是 based on 这个 x 呢，它不是 based on 那个 sequence 的那个 n，
epsilon，你一个
就是
sequence of epsilon 就给你一个 sequence of n 了啊，不对？你考虑一个 sequence of epsilon 过后，每一个 epsilon 都送你一个点啊，y1、
对，
y2，对啊，没
但是
什么问题。
这个 x 呢，怎样讲？我有 x 1 然后我
对
这样就一定给一个 y
对，
x 1嘛，
没有错。
但是
但是
呃，
什么问题？
我这样讲，
还有1分钟，
不好意思，
我问两个问题。
等一下先结束过后，现在没有时间。对，
你呀，就是我
要开始了。
怎样知道一定会 build 一个 sequence，就是我只有这个点
你是说讲为什么 epsilon 会 form 一个 sequence 啊
啊，前 build sequence，我只
？OK OK OK，这样的话你要 build 2次哦。这样你先拿一个 epsilon，然后怎样去找 epsilon 一，怎样去找 epsilon 二，零跟 epsilon 一里面又有 epsilon 二嘛，找另外一个在门之间的，这样子之间哦，你在这边要 apply 一次那个 density 先哦，然后再用这个 epsilon 的 sequence 去 build 一个 yn 的
要一
sequence 哦。
个持续变小的 x，
持续
对，你是问我持续线变小的 epsilon 从哪里找是吗？
不是
持续变小 epsilon 里面会给你一个点一个点一个点扣过去，所以你还把你那个点里面 point。
然后开始，
一个持续变小 epsilon，你永远找得到点的话，
等下再问，
这是一个
结束过。李迪亚回来吗？啊，他要回来吗？换语言。Hello. Hello. Okay, let's start. We're gonna go to the next section, which is functions on varieties. Yeah, finally we talk about functions between varieties here. Before we go in between different affine algebraic set first, we will go to a simple affine space. So let's start with the affine algebraic set. Okay, AN. Okay, so first, there are a few terminology here I need to distinct them. Okay, so first terminology is what we call a polynomial function. Okay, polynomial function. So polynomial function is a function on V, okay, on the affine algebraic set. It's a map. And map from where to where? Okay, so this map is going to the ground field. Okay, so ground field, in other term, there's another name for it, right? It's just A1. Okay, affine one space. Okay. Okay, so going to ground field, polynomial function referring a map to ground field, such that there's this polynomial f in your polynomial ring. Okay, your polynomial ring could be n variable, okay, such that for every point in V, when you evaluate your map, okay, when you evaluate your map, actually you can use a polynomial to evaluate it. Okay. So this just says that your polynomial function can be written as a polynomial form as well. So that's why we call it a polynomial function. 看得懂吗? Does it make sense? This definition. Okay. I don't use dot equal here. Bear in mind. I use equal. So there's a subtlety here. Subtlety means what? Math, right? I just need to tell you. You give me an input output. I just give you an output. You give me an input. I give you an output. That's all. You understand what I said? There's a subtlety here. You need to understand. For example, let's say I want to define a function. Okay, f that sends 0 to 0, send 1 to 1, send 2 to 4, and then f send to minus 2 to 4 also, right? So you can try and give me a formula. Maybe one of the formula you give me is maybe f x is just x squared, maybe. Because I will tell you all the other points. Just that this 4 point, you will see that they match. Okay, so when we say equal here, you need to check at all points. Every point you check. Okay, in principle, f is just the left hand side. Okay, between domain and codomain, how you send them? It's arrow. It's basically just arrow. Okay, how do you send them? Okay. For example, like 0, 0 here, 1, 1 here, 2 here, 3, 3 here, 4, 4 here. So this is really basic, I would say. Okay, I'm not sure you have seen max in this kind of context. You should have seen it. I would say that -2 gets sent to 4, 2 gets sent to 4, 0 gets sent to 0, 1 sent to 1. Yeah, something like that. Okay, could be x squared this function, but who knows? I will tell you where the other functions, where the other domain point gets sent to. So if they are equals, then we will call it a polynomial function. Okay, make sense? Obviously, all polynomial is a polynomial function. Fair enough. So maybe, yeah. What? All polynomial should be a polynomial function. Okay, next. We're gonna define a very cool stuff. Okay, which we call the coordinate ring. This is a very cool stuff called the coordinate ring. So coordinate ring, we will denote it by the field adjoint a variety. Here adjoint V. Okay, affine algebraic set here of V. How do we define this? we cannot run too far from the affine space, okay? We cannot run too far. Okay, so this KV here is defined by, so I use the dot equal here, is defined. Okay, you don't know what is it, I define it for you now. So it's the n polynomial ring of n variable quotient by the ideal of this variety here. Okay, perfectly good quotient ring. So in particular, what this wow, I cannot say that, right? So that's what there's a projection from the polynomial ring of n variable into this quotient ring. I cannot say that this ring sit inside the polynomial ring of n variables, right? Because they are different. Ring. So basically, how do you think about this? Do you know how to think about quotient ring or not? Okay, you have these the big ring in the denominator. What does a quotient ring do? You partition your set using this IV here. Okay, as long as they are different by an IV, they are the same. An element in IV, they are the same. Okay, whole set of IV. Okay, so maybe we make a very quick remark. So why do we define this ring as such? We'll say that this ring really makes sense. Okay, this really describe all the function of V. Okay, why? Because if we take any function from the big ring here, an, okay, and then if you restrict to V, what happens? Restrict both of them to V, what happens? Okay, if these two happen to be the same thing on this variety here, this is only true if their difference restricted to V is also 0. But what does this mean? This means that actually f minus V is differ by a function, an element inside this ideal. Why? Because what? Function of IV vanishes at every point in. But you not understand what I said. So meaning f minus g could be some function. This function restrict to V must be 0. Meaning what? This function will live inside the ideal generated by. Okay. They could have some non-zero difference here, but evaluate at V it is 0. So meaning what? This function vanishes at V. Vanishes at V, you must include into the ideal generated by correspond to this variety. Or this affine algebraic set. Okay or not? Okay. Okay, so maybe I make a remark here. So this is a difference live in IV. That's all. Actually, this is what I write inside. I write as a mathematical term here. Whether you can read it or not is another story. And so the difference here, I have to take inside IV. Okay? Yeah. Well, so why we call it a coordinate ring? Where's the coordinate here? To you, what is coordinate? What is coordinate to you? XYZ. Yes. Okay. So this ring actually are generated by this function here. So these functions are called the coordinate function. So what are the coordinate function here? Is the function x1 up to xn. Where you see it as a function. Function. What does the function do? Do you know what does this function do? Well, just now, okay, now again test you. So our function consider from where to where? From V. V live in where? These are affine algebraic set, right? Live in affine space. Okay, so maybe AN in our case. Go to where? Evaluate to the ground field, which is also equals to A1K. So if you are a point living in ANK, right, what does it mean? We know how does the point in ANK looks like, right? It's what? A1, A2 up to AN. So what does X1 do? What do you think? What can your coordinate function do? You just read out the I coordinate. So in this case, you read out the first coordinate. That's all. So this is one of the coordinate. It's a bit like projection. Yeah, projection, yes. Yeah, you can think of it as a projection. Okay, no. Okay, but the subtlety here is we are looking at the variety, not the affine space. We look at the variety. Get the variety. Okay, random variety. Yeah, random variety. So first proposition you can immediately draw is if V is irreducible, what can you say about KV? What can you say about KV? Saya. If V is irreducible, what is IV? IV should be, sorry? If your variety is irreducible, what can you say about your ideal? 三种选一个 radical prime maximum. 听不到大声一点。Prime 谁讲你讲谁讲刚才讲 Prime？ 你讲哇，你声音不一样哦，大声一下，大声一点。OK， 声音好听要大声一点。Sound is good. So if IV is prime, what can you say about KV? You are quotient by a prime ideal, meaning what? KV is an integral domain. Okay, it's an integral domain here. So, again, we can have a bijection theorem here where we restrict to KV. So you can ask a similar question here. If I quotient out my quotient, I mean the affine space, just now we talked about radical, maximal, and prime ideal in the affine space, right? Now you're talking about quotient of affine space. We also can talk about radical ideal inside here. We can also talk about prime ideal inside here. Okay, similarly, we can talk about maximal ideal inside here. Okay, so do you know what's the relation between this ideal inside a quotient ring with the original ring or not? You still recall what's the theorem between these? What's the theorem we can use between a ring and a quotient ring? There's also one-to-one correspondence here. Correspondence theorem. Okay, correspondence theorem. Yeah, very nice, very good to use here. Okay, so this correspondence theorems, right, will help you to prove that this set will also have one-to-one correspondence of what? Let's say radical ideal is correspond to the closed set in V also, and then irreducible prime ideal here also correspond to the irreducible set in V, okay, and then maximal ideal here correspond to the point in V. So you can show that the projection, okay, or the residual map inside the correspondence theorem will preserve the property of being radical, prime, and maximal. Okay, so then you can look at it back in your original affine space. Okay, so here we say that use correspondent here. Okay, on this projection map here, pi from AN to KV. So this is a generalization of what we get from the Hilbert-Nonsteller. Hilbert-Nonsteller, we only talk about ideals in the R-finite space. But here, we talk about ideal in the coordinate ring. And just study the function space on the variety. Okay, function space on the variety. So you could imagine, right, because your variety already satisfies what? Is a zero set of some function, right? So you could imagine that if I can plug a different function onto this function that vanishes from this point. Give you another function. And then you want to ask this function and the other ordinary function has different look. Okay. So okay, maybe I add something. I will preserve. I preserves. Right. Preserve properties. Ideal properties. Okay, preserve ideals property being radical, prime, and maximum. Okay, yeah, so you should check it. Okay, next, we'll call an algebra A to be reduced. Okay, reduced means what here? So if A contains no nilpotent elements. Okay, new here means zero. Okay, potent here means power. So how to put zero and power together? So that is for every x in this algebra here, if xn equals 0 for some n greater equals 1, then we don't want the non-zero x to appear. S can only be 0. Okay. There's nothing that gets to 0 with some power other than 0. Okay, if this x is non-zero, we'll call it a nilpotent element. Because it is non-zero, but taken to some power, it becomes 0. Then nilpotent. Nil after some power. Then nilpotent. Yeah. Okay, so first proposition is the coordinate ring KV is actually nilpotent. Sorry, it's always reduced algebra. Okay? It's always a reduced algebra. Okay, why? Actually, this property here is quite related with being radical, right? You quotient out by some radical ideal. Correct or not? Radical ideal says what? F such that there exists some n such that Fn live inside the original ideal. Okay. But you quotient by radical ideal means what? This Fn here is 0. But you kill all of them. So you kill all the nilpotent elements. Okay. So what's the proof here? Okay, so the proof here is the algebra xn quotient by I is reduced. Okay. If and only if you kill all the nilpotent element, which is the radical ideal. Okay, you kill all of them. The non-zero one. Okay, that give you Fn equals 0. Correct. Okay, you kill all of them. Okay. Why? Because the algebraic set we consider the I that attached to this V should be always radical. This is by the Hilbert-Lonsdale method. Okay, so you always kill it by a radical ID. Okay, so given any affine algebraic set, right? The ideal that define this affine algebraic set is always radical. So you take away, you kill all the radical elements. Okay, any question or not? Okay, maybe look at some example of reduced algebra here. So let's look at some example of reduced algebra here. So first is parabola. Okay, parabola here. So parabola is what? We can call it C0, such that this is a zero set of y minus x squared. Y minus x squared, the usual one. So what do you think was the coordinate ring that correspond to this guy here? So we call it K adjoint C0, right? How is it defined? Which affine space you consider here? How many dimensions? Affine? 1, 2, 3, 2. Okay, so K adjoint XY. Quotient out by what? The ideal generated by y minus x squared. Okay, but what's this isomorphic to? Can you recall or not? Y, you make y into x squared already, right? So meaning everything could be generated by x. Okay, so actually, this is isomorphic to K adjoint x. Okay, so K adjoint x is just what? Equals to A1. A1, sorry, not this A. Polynomial ring with one variable. Okay, but at the same time, what? This is isomorphic to K adjoint A. So K adjoint the affine line. Okay, correct or not? And what's the ideal that define this real line here? What's the ideal that define this real line? What's the function that vanish at every point? And what's the function that vanish in every point? Still remember Zariski topology. What's the function that vanish at every point? You shall constant vanish at every point. Constant, nothing. Depend on what constant function you have, right? If it's 0, then every point vanishes. Is it correct? Correct or not? So you have a constant function 0 every point vanishes. Yes. Yes. Is it correct? What's the Zariski topology? So the first two segments you get, what is it? You have to discuss. Okay. Am I writing something wrong here? So what's the ideal? What's the ideal of so I'm thinking of this quotient out by an empty set. So who gives this empty set? I of 1. I of 1 is an empty set. I should quotient by 0. Oh yeah, sure, you are right. So this is equivalent to okay, let me write down first. So if you have a ring, right? So actually you can do some trivial things, right? This can be quotient out by 0 ideal. You recognize this? Meaning the difference is a 0 lah. So that means f minus g is 0. So f have to be equal to g in the original element. Don't know this I make this into a exercise inside your tutorial. You should know this. This is very simple. First thing you should know the thing about quotient ring. Go back and think about it. Yeah. Okay. But just now we say that who defined this ideal? Which variety defined this ideal here? Is the whole space, no? Here's the whole space. Okay. So what can you see here? In y minus x squared here is a line actually. But on the right, on the left hand side, the coordinate ring also isomorphic to a coordinate ring of a line. Okay, meshes with your intuition. Okay, on this side here, coordinate ring, this KC0 is isomorphic to a coordinate ring of a line, affine line. But parabola here also an affine line. Sure, yeah. Okay. Second, a non-trivial one. So let's look at semi-cubical parabola. This C1 here is, let's say, Z of y squared minus x cubed. And you can try and plot this out, at least in the R locus, real locus. What's this coordinate ring here? So what is K of x1 here? K of x1. So this is just kxy, quotient out by the ideal driven by y squared minus x cubed. Okay, not that this guy is not a UFD, and not that this guy is not UFD. I think later we will do something special on these two guys. Yeah. Okay. Let's go on. We still got 8 minutes. Now we just now we define a polynomial function, right? Now we're going to define a polynomial map. Okay, so this is a map between two algebraic sets. Two algebraic set here means the codomain could be something else in a different affine space. Okay, instead of just A1. Okay, instead of just A1, we can go to a different algebraic set in a different affine space. So how we're going to define this? Obviously, we will define based on what we know about polynomial function. Okay, so now we're going to define a map from V to W as calling as the polynomial map. Okay. Okay, so reckon that this map and this map has nothing to do with each other. Okay, this is just a special name, polynomial map, referring that this function here is going from a V to a random W. Now, obviously, you can call the previous polynomial function as a polynomial map. We will see soon. Okay. So what is this polynomial map here? So if there exists more polynomials now, f1 up to fm, because you need to cater for what? You need to cater for the dimension of your codomain here. Okay, your dimension of the codomain is m. Okay, you need to produce m number here. Okay, you need to produce m number here. So such that for every point in your domain, okay, your fp should coincide with the component map f1p, f2p, and then up to fm. Okay, does it make sense? Okay, so meaning we make a multiple of polynomial map, a polynomial function together into a polynomial. Okay. Okay. Give you examples. Actually, just now we give you a very obvious example, right? So those are the polynomial function. Polynomial or polynomial function, if we have change the name. So polynomial function is from where to where? From x to k. Okay, which is a1k here. Okay, so polynomial function is a polynomial map. Okay, what else? Your linear algebra, any linear map. Okay, linear map from an to am. Okay, So learning the algebraic geometry really includes linear algebra. Third, what else? Very obvious map one. If we fix NM as such, then we can consider the projection inclusion. Okay, projection inclusion. Because these are built by the coordinate function. Okay, coordinate function is perfectly good polynomial. Okay, perfectly good. Okay, you can project from the larger space, greater dimension space to a smaller dimension space, and then you include from a smaller dimension space to a larger dimension space. There's a particular kind of map you want to look at, which is the R5 map. Okay, so what's this R5 map here? Also come from linear map actually, but this linear map have a special form here, which is x sending to ax plus b. Okay, so this is a very special linear map here. So what does this do? What's this A and B here? So this A actually is just some M times N matrix. Okay, might not be invertible. Depend on the size of M and N, and then yeah, you can only ask about invertibility when S and M is equal, in which you get a square matrix. If it's not square, no need to ask about invertibility. Okay. Maybe there's a left or right inverser, but it's not invertible. And what is B here? B is like shifting away your points. Like shifting away your points. So if A turns out to be invertible, okay, then the map x to ax plus b, right? There's a name for it. What's this name? What is this? It is actually a coordinate change, or more precisely, this is a affine coordinate change because we are doing on the affine. Okay. Okay, coordinate change. So maybe you rotate, you scale, and then you move it away. Okay, yeah. Very familiar, huh? Yeah, it's precisely what you are talking about last time. Okay. Okay. Big part here. Let's look at a very concrete map. So let's say we got a affine line here, and then we want to map into, just now there's a semi-cubical parabola here. What do we do here? This is calculus 2a. One variable into two variable that describe this line. What do you think? T should go to where? Well, let's do an easier case. So let's recall your knowledge. Y equals to x squared. Right. How do you parameterize this? T goes to where? T and T squared. How about the one above? T cubed T squared. T cubed T squared. Let's try first. So if I put a T cubed here and then T squared, is it correct or not? Does it satisfy the no? Sorry, change that. T squared and T cubed. Okay. Yeah. That's all. In particular, parameterization is one of the polynomial map. Actually, it's one of the very important one that you want to look at. Okay. One way to see how to see it is a polynomial map. I think see from this polynomial parameterization, you will already guess that a map f v to w is a polynomial map. How to check? You need to check that every coordinate can be defined as a polynomial, right? So meaning what? You need to project your f first to every component such that it is equal to some polynomial. Okay. So if fj equals to yj on f, and then this fj here should be some polynomial. Okay, living in this coordinate ring for all j in 1 to m, where this yj is a coordinate function. Okay, I think we don't want to. Do we want? Should we? Should we? Okay, let me do that. I'll prove this in the next lecture. But does it make sense or not? Okay, if you want to check that whether one thing is a polynomial map or not, the definition says what? Every spot there must be a polynomial, must be described by a polynomial. In other words, you project to look at every single column there must be a polynomial. It must be like fj living in the polynomial. Okay. Okay, so this is a lemma. Can try and prove it first, huh? Try and prove it first. Do some homework, then come, and then you won't get so confused. Okay, do some homework. Yes, question. Why there dot f? This dot here, not product. This is the circle here. Okay, CIRC. Slash CIRC. Also. Okay, composition, not product. Okay. All right. See you.